So hello and welcome to my today's talk. Today I will tell you a few things about things regarding memory in Go that is good to know. Today's agenda is, first I'll have a smart introduction of myself, then I'll go with data padding, next escape analysis, followed by a few examples of it, tools that you can use to check your execution of your program, to trace your execution of your program, and I'll finish my talk with short summary. My name is Dawid Gacek. I work currently in SolarWinds. In IT industry, I work for 6 years, more or less. And through that time, I was writing code in Go, Python, JavaScript, and Groovy. I work in digital experience monitoring area, so if any of you know Pingdom, I'm working on newer version of it. Regarding my hobbies, I love running. I run a few times per week. I participate in competitive races, so if any of you runs as well, see you on starting line. Other hobbies are baking bread and playing PlayStation if I have some time. Today I will talk about the things that are related to memory in Go. I work in IT industry, but I didn't do computer science studies, and I always felt like I missed some knowledge regarding stacks, heaps, and this sort of theoretical stuff. Today I'll cover the things that can better visualize and can help you to understand what's happening under the hood when you write your code or you program and execute them. In fact, this presentation is not about telling you what to do or not to do. In fact, you can write 100% correct and executing and very fast code without remembering a single information from this presentation. But understanding these topics or remembering about this topic can give you better confidence about the code that you write. This is the case for me, for instance. And I think that this is the spirit of this code that some of you probably heard already. You don't have to be an engineer to be a racing driver, but you have to have a mechanical sympathy. So let's start with data padding. Computer stores memory, such as data and functions for immediate use in computer. This is the quote from Wikipedia. For this talk, when I tell about memory, I mean random access memory. And the two characteristics important for these talks are that the memory has addressable units that stores bytes, and each memory address is unique within the address space. The most efficient storage is achieved when the data is naturally aligned. Natural aligned means that the address of data, the data starts at the address that is multiple of the size of data. Runtime expects the data to start at this point and searches only at this point. So if the next memory address or next free memory address is not multiple size of the data, there is a need for inserting data padding bytes. So there are empty bytes are inserted into memory. The examples are that for Boolean, we can insert it into every single memory address, but float 64 cannot be placed in every memory address. It can be placed on 0, 8, 16, and so on, if I use the simplification of the memory addressing. So in your memory, you won't face this situation that float 64 starts here. you will face rather this situation. We have control over that. We control how the data is stored in memory, and we control it by definition of our struct. So the same order that we put in struct is reflected in memory. So if I define the struct with the Boolean at the first place and float 64 at the second one, there is a need of 7 padding bytes because the Boolean can fit into first memory address, but float 64 needs to go to the 8th one. Yeah? So we need to place these 7 padding bytes. Runtime places it. There is also another few of padding bytes at the end. This is because the whole struct needs to have a size that is multiple of the biggest data that the struct contains. So if we have float 64 that is 8 bytes, the multiple of it is 24. Few padding bytes at the end needs to be placed. But if you think about it, we have like 13 bytes of data, because bool is 1 byte, float 64 is 8, and float 32 is 4. And we use 24 bytes of data to store it. This is a little bit, this is loss of the data, like we could do better. In fact, there is, if we know that we control it, there is a rule of thumb that says we need to structure our objects from the biggest to smallest to achieve the best memory arrangement. And now the data takes only 16 bytes, and you can see that we don't have to have so many padding empty bytes. We need only 3 at the end. The data density in this case is bigger. So if we have a slice of such elements, we don't lose so much data for empty bytes. So please remember about this data density, at least until the next slide. Yeah. And CPU, our computational unit, relies on caching to speed up the memory access. Usually it's three levels of caches, and the lower the level, the faster the data access is. With the same time that we can read 100, we can reach 100 times the level 1 caches, we can reach the main memory only once, more or less. It's up to that point. So you can see that reading caches are faster. And we read the data from memory by cache line. So if we want to make some calculations over array of data, so we want to iterate over elements, this is what happens. We enter our loop and we hit the level 1 caches, but it is a compulsory miss because the data is not here yet. So we hit the main memory, we get cache line. This is stored in level 1 caches then, and we can iterate over elements included in that cache line. Depending if this is all the data that we needed is stored in the cache line, we can finish the calculation, or we need to fetch another one. This is simplification, of course, but the important thing is that with the more dense structure that we can achieve with proper memory arrangement, we can fetch more items with single cache line. So the data padding is not only about storage and like saving of storage, so we can use less place to for a data struct, but it can be also about speed. That's it about data padding. Escape analysis. Escape analysis, when we work or we run our program, we can store our data either on stack or on a heap. Stack is some sort of default memory. It stores the local variables, and it's self-cleaning. This is important for this presentation. However, the heap is the pool of memory shared by all Go routines. So all Go routines can ask the heap for data, but it needs a garbage collector for cleaning. The garbage collector is a really good thing, but the thing is that it consumes our CPU, and there are microseconds of stop the world at the beginning and end. So when the garbage collector fires, everything is stopped for microseconds of time. Escape analysis is an algorithm that decides where the data should be placed. So if it can be by default placed on stack, or if it needs to go into the heap. The construction of value happens only once, yes? So the escape wording may be misleading here. There is no escaping in the manner that construction happen on stack, and immediately something is escaping. Now, if the algorithm says that it escapes, the construction happens only once on heap. Only construction on heap is called an allocation in Go. And we need to be aware of that only because there is a potential of garbage collector workload, yeah? So if we have too many escapes, garbage collector has more things to do. If we want to check if something is escaping to heap, during our compilation or actually build, we need to pass a gc flag -m to our build command. So this flag outputs compiler optimization decisions. You can also use the higher verbosity level, but the number of output you get may be pretty overwhelming. This is the sufficient level for this talk, so we get few info together with the info about escapes. So to familiarize ourselves with the output, I wrote a very simple code. This is actually only definition of struct with two constructor functions, and one is returning a value, and second one is returning a pointer to value. And I run it with passing the flag. What we can see in the output of this command is that compiler says that it can inline few functions, yeah? Inlining means that Go compiler can copy the function body and put it in place into where it is used. So small hint here, write simpler function, and a compiler may also optimize your code. The next actually 3 lines are that the compiler made decision that these functions will be inlined. Then from the 12th line, pointer to my data escapes to heap. So this is the output that we searched for, and returning pointers to data are one of some sort of common cases that makes escapes. For this example, however, we also have an information that in 19th line, this pointer to my data doesn't escape. This is because of inlining, so the body of function was copied, and there is no need for escape in this particular case. Common example scenarios are returning pointer from function, conversion from strings to bytes, using closures that capture local variable, value assignment to interface or returning interfaces, returning arrays of unknown size, and when the slice grows beyond its capacity. And I'll dive into few of them, few examples. Strings and bytes conversions are pretty interesting to me because they may be overused for our own convenience. For me, I am a human. For humans, I think it's easier to understand the concept of string rather than slice of bytes. And if we want to have some sort of manipulation on text, we may have a tendency to convert it to string, then do some text manipulation, and then convert it back. Yeah, so I/O mostly works on bytes, and when we have this flag that we may gain something here, please remember that the bytes package also contains most of the function needed for text manipulations, for slice of bytes manipulations. I pointed that this is only flag. I'm not telling you definitely don't do strings conversions. Just remember about that. Another example is appending to slices in a case that the slice is full. So when the length is equal to its capacity, what happens in that case is that the new slice is being created, usually with double size of the first one, and all the elements are copied to the new one, and the old one, depending on where is it placed, may need to be cleaned. If we know the size, or we can guess the size in any way, we can pre-allocate the array by, for instance, by two methods, by passing a length to the make, or we can also do it by capacity. Pre-allocating by length creates a zeroed values of elements, while capacity only reserves a memory for the data. These two are similar in terms of speed. Create by length is a little bit faster, but for some people it may be more cumbersome, or it may be less readable because of this indexing size. And both these two scenarios, I think it was example about 1000 length slice, are about 4 times faster compared to not allocating. Returning interface, I don't know if I'm only one here, but I was truly believing that there is a Go proverb, accept interface, return struct. The Google style guide mentions about accept interface, return concrete types, but I found that the Rob Pike is actually saying it cannot be distilled into proverb, because there are multiple scenarios where you may want to accept interface and return an interface, or even accept struct and return interface. So this is not the case. This is not proverb. But when we limit our point of view for only the memory point of view, with the interfaces, you get some sort of overhead because there are some pointers to itab and data table. And usually they go to heap. There is, I have another example. This is about API design. And the example is about reader interface. Reader, if I was designing reader, I'd probably understand that we want to read something, we want to output some string or slice of bytes, but I would initially think that it will be maybe better to implement it that way. So to output the slice of bytes. And we are lucky that I didn't design it, because in that way, there would be 100% allocation. So we return the data of unknown size. The Google decided that this version is better. This is passing the slice of bytes into the function. And thanks to that, how to say it, the decision if we should allocate or not the slice of bytes is up to the implementer or caller of this interface. Otherwise, like this way, it would be 100% allocation. This is all about examples. I will go to those in a minute. Okay, so if you want to go to your code and check all your structs for potential savings on memory, you don't have to do that. There is a linter for it. So this is about data padding. It's included in GoVet. So what you have to do, you have to enable it. And if you want to save some memory because of anything that you just want to, you'll get output that you can do it better. Regarding escapes and tracing execution, you have few options. For me, the easiest, the fastest one is to check it by passing or setting the GoDebug environmental variable to gctrace equals 1 and running your program. Maybe good to compile first, because if you don't do that, you will also get the output for garbage collections for compilation step. But the very good pro of using this function that you don't have to add any code, any additional code to your code. You just run the command with environment variable set. So this is just running. So go run main.go. You can see that there is output for compilator as well. Building and running executable yields only garbage collection info. And we can very quickly check if the garbage collection even occurs. So we have the occurrence of, so what does it mean? The first numbers mean that it's an occurrence and the time of occurrence. And the percentage of execution of program that is spent in garbage collector phase. There is also other info, but I won't read all of this. It is covered in documentation. It may change with versions, so you can find it easily. If you want to check some specific codes regarding memory allocations, you can use a runtime or the debug package. All you need to do is to define a respective memstats runtime.memstats variable or the debug.gc stats, and read into that by passing the pointer to this variable. Yeah. With that, you get number of output, like number of GC cycles, allocated memory, total allocated memory. If you need to check some points in your code, you can do it that way. And the last tool that you can use is the most sophisticated maybe tool, because it can visualize us what's happening in our program. It is GoTrace tool. There is number of possibilities that you can run it. So you can add a trace.start and pipe it to pass the writer of std out. Then you have trace output under standard output. So you need to pass it to write it in pipe it into trace out file. And you need to visualize it with go tool trace and the name of the file. You can also have your traces output from running a test. You need to pass a -trace and the name of the file. I think for benchmark there is a similar command. And this beautiful site, when you run this tool, this beautiful site will open in your default browser. You can navigate by these two links to such visualization tools. It contains your execution. So you can, through whole the execution of your program, you can see the number of Go routines, heap, number of threads, the heap, like the heap that is used, and the goal heap. You can see the garbage collection runs, and you can zoom and manipulate, like move around to check it in details. There is something more in trace tool. If you have some specific area regions that you want to look at, there are concepts. There are concepts of task regions and logs that you can add to your trace output. And for visualization of that, I also made small code. This code is just running 10 concurrent HTTP GET calls to google.com. So I added a task that's named 10 Google calls. Yeah, the concept of task is somehow higher in the hierarchy, so it can span over few Go routines. And the region that I marked here, so inside the Go routine, the region is a little bit lower in the hierarchy, so it should be inside one Go routine. It shouldn't span across a few Go routines. And for example purposes, I added a trace log that is outputting the number of iteration. If you again run this trace tool, you will be a little bit lower on this side. You will see two other navigation tools, navigation links. And if you click them, you'll see a table of your task execution. In my case, it was only one execution, and the region's execution. There was 10 execution, and you have the histogram of timings. So for instance, I can see here that there was 4 executions between 158 and 251 milliseconds. If you explore your task further, you will see the logs. Yes, so the logs with your marks, the timestamp, the time that elapsed from previous from previous logs, and you can also navigate to visualization that is bounded by your task definition. If you choose the number from the table of our task definition, there will be another table with your every execution, and you can also navigate it from here to the visualization table. And if you want to check the call graphs or network profile, you can go inside it. So that's it for today. Today I was talking about data padding. If you didn't know about it, I familiarized you with the memory arrangement in your program, in programs in general, in Go. Then I went through escape analysis with few examples, and I showed a few tools that may be useful for you. And I want to emphasize once again the fact that I didn't meant to tell you what to do or not to do. These were rather optimization topics. I hope you will not ever need to use that tools because using them is harder than just showing them. If you need to use these tools, you probably have some sort of bigger problem, and probably the only case that you want to use that knowledge very deeply is because your benchmark told you that you need to do that. So with that, I'd like to thank you. I hope you learned something new, or at least it was interesting.